Welcome back to the channel, where we crack open the biggest mysteries in the universe. Today, we are diving into a war zone for our minds, the front lines of theoretical physics where general relativity and quantum mechanics collide. For almost a century, scientists have been staring at the same wall, trying to make gravity fit into the quantum framework that governs everything else. We will explore how Roger Penrose and others mapped these unsolved problems, why current theories like quantum field theory fail when it comes to black holes and singularities, and what a recent breakthrough from London-based physicists might mean for our understanding of reality itself. By the end of this video, you'll understand exactly where we stand on July 13th, 2026, and why the next 50 years could rewrite the textbook on how gravity works. Let's talk about the wall that has stood for a century. In 1982, Roger Penrose published a list of mathematical physics problems specifically targeting general relativity. He didn't just ask vague questions. He laid out specific puzzles involving black holes and gravitational waves. Decades later, in 2017, it was still clear that about 14 of those original problems remained completely unsolved. It is almost unsettling to think that despite having the most powerful computers on the planet and the deepest telescopes ever built, we cannot yet make gravity behave consistently with quantum mechanics. This isn't just a theoretical annoyance. It means our fundamental description of the universe has two separate rulebooks, one for the very small and one for the massive, but no way to translate between them. Enter Ivette Fuentes, a professor of quantum mechanics who spends her time at scales where these two worlds actually touch. Her work highlights the experimental gap we are facing. While we can test quantum theory down to subatomic particles with incredible precision, as soon as you try to apply those rules to gravitational fields, the math breaks down. We have 7 massive unsolved problems in physics today, according to a tour by Daniel Whiteson from UC Berkeley, and gravity is the elephant in the room for all of them. The core issue is that quantum field theory describes particles interacting via forces like electromagnetism or the strong force, but it treats gravity as just another background stage rather than a dynamic player. When you try to quantize gravity directly, you get infinities everywhere that no amount of mathematical trickery seems to eliminate without changing the fundamental nature of space and time itself. So how do we explain this without quantum field theory? David Tong, a theoretical physicist known for his clarity, has pointed out that while our current framework is one of the most accurate concepts in science, it simply leaves classical gravity on the table. It works perfectly for particle accelerators and atomic clocks, but it fails spectacularly when you look at a black hole or the early universe moments after the Big Bang. In those environments, spacetime isn't just a smooth fabric. It is vibrating, tearing, and folding in ways that standard quantum field theory cannot describe, because it assumes a fixed background stage for the actors to play on. This limitation becomes apparent when you try to measure gravitational waves or understand the interior of a black hole. The equations predict singularities, points of infinite density where physics as we know it ceases to exist. If gravity were just another force mediated by particles, like photons for light, we would have a theory of quantum gravity already in hand. But because gravity couples to itself, the interactions become infinitely complex at small scales. This is why the holy grail of physics remains elusive. We need a new framework that doesn't just patch up quantum mechanics or tweak general relativity, but unifies them into a single coherent narrative. Until then, we are left with a duality where our best theories coexist in separate rooms, never allowed to interact. Now, here is where things get truly fascinating and perhaps controversial. In November 2025, a new discovery suggested that gravity might not exist at all in the way we have traditionally thought. 2 London-based physicists challenged the very premise of how quantum fields operate alongside classical gravity. Their argument suggests that our current understanding of gravitational forces as distinct entities emerging from spacetime curvature may be fundamentally flawed. Instead of viewing gravity as an interaction between masses, they propose a perspective where the distinction between quantum fields and classical gravity dissolves under certain conditions. This idea requires a complete overhaul of how we think about reality. If gravity is not a force mediated by gravitons traveling through space, but rather an emergent property of information processing or thermodynamic constraints at the horizon of black holes, then all our calculations regarding gravitational waves and orbital mechanics might need reinterpretation. It is a bold move that risks alienating traditionalists who cling to Einstein's equations as absolute truth. However, if they are correct, it opens up entirely new avenues for solving the unsolved problems Penrose identified decades ago. Instead of trying to quantize gravity, we would be looking for the underlying code that generates gravitational effects from something far more fundamental. This shift suggests that the missing piece has been hiding in plain sight all along, disguised as a problem with gravity when it is actually a question about the nature of information itself. Why does any of this matter to you? The answer lies in the practical takeaways and surprising insights hidden within these abstract concepts. If we can finally solve the puzzle of quantum gravity, or if we adopt the new perspective that gravity is emergent rather than fundamental, it will revolutionize energy production, computing power, and even our understanding of consciousness. Imagine a technology that harnesses the energy of black holes without the destruction, or a computer architecture based on quantum gravitational principles that operates at speeds far beyond our current silicon limits. Furthermore, this research has immediate implications for how we observe the cosmos. As we look further into deep space with the James Webb and future telescopes, we will encounter events that can only be understood through a unified theory of gravity. From the birth of stars to the life cycle of galaxies, every celestial event is a test case for these theories. The fact that we are still debating whether gravity exists in its classical form means our maps of the universe have blind spots that could hide new physics waiting to be discovered. By engaging with these questions now, scientists like Whiteson and Fuentes are not just solving equations. They are building the infrastructure for a future where humanity can manipulate forces currently thought to be immutable. The journey from Penrose's lists in 1982 to today's challenges in London shows that, while we haven't cracked the code yet, we are finally learning how to read it. So, there you have it. From Roger Penrose's century-old list of unsolved problems to the radical suggestion that gravity itself might be an illusion, the race for a theory of everything is far from over. We've seen where quantum field theory hits its limits, how recent challenges are reshaping our view of spacetime, and why solving this mystery could change everything we know about the universe. If you found these insights compelling, smash that like button and subscribe for more deep dives into the unknown. Drop a comment below telling me which problem is your favorite, or if you think gravity really doesn't exist at all. We'll see you in the next one.